For centuries, we have looked up at the night sky and seen our own solar system as the blueprint for planetary architecture. We knew our small, rocky worlds like Earth and Mars, and then the colossal gas giants such as Jupiter and Saturn. This seemed to be the universal cosmic rule, a fundamental dichotomy of planetary existence. Yet, what if the very framework of our understanding was incomplete, missing the galaxy's most dominant residents, right here in our own cosmic backyard? What if the true standard for planetary systems was staring us in the face, absent from our immediate surroundings, making our home a profound and unsettling void in the statistical census of the universe? The profound shift began not with distant probes, but with a technological marvel launched by the National Aeronautics and Space Administration. In the early 2010s, the Kepler Space Telescope, under the visionary leadership of principal investigator William Borucki and his dedicated team, ushered in a data revolution that utterly shattered our provincial view of the cosmos. For years, the telescope meticulously stared at a single patch of sky, observing the subtle dimming of starlight, a tiny flicker that betrayed the presence of worlds far beyond our reach. Each dip, each transient event, was a clue, and as these clues accumulated, a startling truth began to emerge. Thousands upon thousands of exoplanets were catalogued, a number that grew exponentially, revealing a planetary population far more diverse than anyone had imagined. But the true revelation was not just the sheer quantity, it was the sheer prevalence of a type of world that simply did not exist in our own solar system. These were planets larger than Earth, but significantly smaller than Neptune, fitting into an intermediate class that had, until then, been largely theoretical. Scientists soon named these enigmatic worlds super-Earths and Mini-Neptunes. Suddenly, the planets we thought were standard, our familiar Earths and Jupiters, were revealed as cosmic rarities. The vast majority of detected worlds, the default outcome of planetary formation across the Milky Way galaxy, were these super-Earths and Mini-Neptunes. It was as if humanity had studied only elephants and mice, only to discover that the forest was teeming with creatures the size of bears, yet none had ever ventured into our garden. This discovery forced astronomers to confront a startling inversion of perspective. Our solar system, once considered the archetypal example, was in fact the anomaly, a cosmic outlier in a universe teeming with different kinds of worlds. The initial shock among the scientific community was palpable. Decades of planetary models, built upon observations of our 8 known planets, were suddenly incomplete, if not fundamentally flawed. The very definition of what constituted a typical planet had been rewritten, not by a single dramatic discovery, but by the relentless accumulation of statistical data. Planetary science transformed from a focused study of our immediate neighborhood into a sprawling statistical exploration of cosmic demography, seeking to understand the true distribution and characteristics of worlds across the galaxy. This fundamental shift in understanding posed the central, most compelling mystery of our story. If these super-Earths and Mini-Neptunes are indeed the galactic standard, found orbiting nearly every star we survey, then why, in the formation of our own solar system, did we fail to produce a single one? It is a question that challenges everything we thought we knew about our place in the universe. We have come to understand that the cosmos teems with worlds unlike our own, the ubiquitous super-Earths and Mini-Neptunes now known to be the galactic standard. Yet, as astronomers meticulously compiled data from missions like Kepler, analyzing thousands upon thousands of exoplanets, a bizarre anomaly began to emerge from the sheer statistical noise. It was a silent zone in the galactic neighborhood, a strange, empty gap in the planetary census where worlds of a certain size simply seemed not to exist at all. This wasn't just a missing data point, it was a profound absence, a cosmic void. This striking phenomenon, often referred to as the Fulton Gap or the Radius Valley, was first systematically identified in 2017 by a team led by Benjamin Fulton at the University of Hawaii. The discovery was nothing short of a bombshell, revealing that the continuum of super-Earths and mini-Neptunes was not smooth and unbroken as one might expect. Instead, it represented two distinct populations, sharply divided by a statistical chasm, a clear line in the sand around 1.5 to 2.0 times Earth's radius. Worlds falling just below this critical boundary are overwhelmingly dense and rocky, their surfaces exposed, their bulk composed of silicate and iron. But cross over this invisible frontier, and the planets just above the gap exhibit a dramatically different composition. They are cloaked in thick, puffy atmospheres of hydrogen and helium, like miniature gas giants. This stark dichotomy, observed across countless star systems, immediately suggested that a powerful physical process was actively at play, sculpting these nascent worlds and relentlessly forcing them down one of two evolutionary paths. It was as if the universe itself was engaged in a grand, cosmic sorting experiment. So, what titanic forces could be responsible for carving out this forbidden zone? Two leading hypotheses are currently locked in a scientific battle to explain this planetary divide, each offering a compelling, yet distinct, vision of cosmic evolution. The first, widely studied, is known as photoevaporation. This theory posits that intense, high-energy radiation from young, active stars, particularly during their fiery youth, acts like a celestial sandblaster. For planets forming too close to their parent star, or those that are simply too small to hold on, this relentless stellar wind strips away their primordial atmospheres, literally boiling them off into space over millions of years. What remains is a naked, rocky core, a denuded super-Earth, baked and exposed to the harsh vacuum. Consider the sheer power of a star's radiation, not just visible light, but the unseen torrent of extreme ultraviolet and X-ray energy. It is a torrent so immense that it can accelerate hydrogen and helium atoms to escape velocity, pushing them out of a planet's gravitational well like leaves caught in a hurricane. This process is particularly effective on worlds with lower gravity, or those bathed in the most intense stellar glare, explaining why planets below the gap are typically smaller and closer to their stars, having lost their original envelopes. But the universe, as always, offers more than one explanation. A second, more recent and increasingly compelling theory is core-powered mass loss. This hypothesis suggests that the heat radiating from a planet's own molten core, the fiery heart of a newly formed world, provides the energy to drive atmospheric escape. As the planet cools and contracts over eons, this internal heat can slowly but relentlessly puff up the outer layers of its primordial hydrogen-helium atmosphere, eventually pushing it beyond the planet's gravitational reach. It is a subtle internal form of stellar stripping, a slow boil from within, rather than a scorching blast from without. Unlike photoevaporation, which is largely dependent on the star's activity, core-powered mass loss relies on the planet's own thermal evolution. This means it can affect worlds further from their stars, or those orbiting older, quieter suns. Scientists are now dissecting the evidence for each theory, examining how factors like the stellar type, whether a fiery O-type star or a cooler red dwarf, and the precise age of the planetary system influence this cosmic sorting mechanism. Each new observation, each subtle signature in a distant world's atmosphere, adds another clue to this cosmic crime scene, transforming a simple graph of planet sizes into a complex narrative of gravitational forces, stellar fury, and planetary destiny. The Forbidden Zone is not merely an empty space on a chart. It is a profound insight into the violent and dynamic birth of worlds across the galaxy. Consider for a moment the very act of looking. What if the tools we create to extend our senses, to pierce through the cosmic veil, inadvertently blind us to the most fundamental truths? For centuries, humanity peered into the night sky, its vision limited by the very designs of its instruments. This wasn't merely a technological shortcoming. It was a profound psychological trap, a mirror reflecting our own preconceptions back at us, creating a skewed and misleading picture of the galactic population. It's a compelling detour into the history of technology and the psychology of scientific discovery, revealing why the revolution in our understanding of planets took so long to ignite. For decades, the hunt for worlds beyond our own was governed by the capabilities of the pioneering radial velocity method. This ingenious technique measures the subtle wobble a star exhibits as an orbiting planet tugs on it gravitationally. It's like watching a distant dancer. You cannot see the tiny partner, but you can infer their presence and mass by the way the larger dancer sways. The greater the planet's mass and the closer it orbits, the stronger its gravitational pull, and thus, the more pronounced the star's wobble becomes, making it easier to detect. This method, revolutionary as it was, held an intrinsic bias. It was exceptionally good at finding massive planets in tight, close-in orbits, the so-called hot Jupiters. These colossal worlds, often larger than Jupiter in our own solar system, screamed their presence across interstellar space, their immense gravity causing their parent stars to swing wildly. It was this very technique that triumphed in the landmark discovery of 51 Pegasi b in 1995, a finding that ignited the modern field of exoplanetary science. Swiss astronomers Michel Mayor and Didier Queloz unveiled a gas giant orbiting its star in just 4 Earth days, a revelation so extreme and unexpected that it shattered every existing model of planetary formation. These gravitational behemoths, the hot Jupiters, were so utterly bizarre compared to anything in our familiar solar system that they dominated the scientific imagination for years. They became the archetypal exoplanet in both public and scientific discourse, shaping our very definition of what an alien world might look like. Our instruments, designed to find these easy-to-spot giants, acted as a powerful filter, showing us not what was most common in the galaxy, but simply what was easiest to see with the technology available at the time. This was a classic case of observational bias, a technological version of confirmation bias, where the very tools we built inadvertently reinforced our pre-existing expectations, which were, ironically, based solely on the unique architecture of our own solar system. To understand this self-imposed blindness, consider a parallel from a distant era. In the 17th century, Antony van Leeuwenhoek, a Dutch draper, ground his own lenses and crafted the first true microscopes, opening up an entirely new, unseen world of microbes. His revolutionary instruments revealed a universe teeming with tiny creatures previously unimaginable. Yet, the limitations of his early microscopes, their narrow field of view, their specific magnifications, also defined the scope of microbiology for over a century. He saw what his tools allowed him to see, and for generations that became the known universe of the very small, leaving countless forms of microscopic life still hidden in plain sight. The story of super-Earths and mini-Neptunes, the true cosmic majority, is therefore not just one of discovery, but of overcoming precisely this kind of self-imposed blindness. It was a journey that demanded inventing entirely new ways of seeing, new technological lenses to peer through the cosmic fog and reveal the truly prevalent residents of the galaxy. This paradigm shift finally began with the perfection of the transit method, famously exemplified by the NASA Kepler mission, which observed the subtle dimming of starlight as a planet passed directly in front of its star. This new perspective would ultimately redraw the map of the cosmos, revealing a universe far stranger and more diverse than we had ever dared to imagine. The sheer prevalence of super-Earths and mini-Neptunes, those enigmatic worlds so unlike anything in our own celestial backyard, presents a profound cosmic conundrum. How could such massive planets form so close to their parent stars, often nestled in orbits where, by all traditional understanding, there simply isn't enough raw material? Our long-held models of planetary birth, based largely on the architecture of our own solar system, stumbled at this fundamental question. The standard core accretion model, a framework that successfully explains the formation of Earth and even Jupiter, struggles to account for these close-in behemoths. In the blistering heat and sparse material of a protoplanetary disk's inner regions, building a world several times the mass of Earth, or one with a puffy hydrogen atmosphere, seemed utterly impossible. Yet, the data from thousands of exoplanets screams otherwise. To reconcile this glaring paradox, astronomers turn to a concept as elegant as it is dramatically chaotic: planetary migration. This isn't a gentle drift, it's a cosmic ballet of immense proportions, where young worlds are anything but stationary. The groundbreaking idea, first rigorously developed by visionary theorists like Douglas Lynn and Peter Goldreich in the 1980s, posits a radical truth. Planets are not necessarily born in the orbits where we find them today. Instead, they begin their lives in the colder, more material-rich outer reaches of their nascent systems, far from the searing heat of their parent star, where ample gas and dust allow for rapid growth. Once these worlds begin to coalesce, their sheer gravitational presence within the surrounding protoplanetary disk sets off a complex chain of interactions. Imagine a colossal celestial disk, swirling with gas and dust, perhaps hundreds of astronomical units wide, far larger than our solar system's current extent. As a young planet grows within this disk, it carves out a gravitational pathway, creating ripples and waves in the surrounding gas. These gravitational tugs and pushes do not cancel out. Instead, they exert a net torque on the planet, inexorably pulling it inward. The young world effectively surfs these waves of gas, spiraling closer and closer to its parent star, drawn by an invisible current of cosmic angular momentum. This chaotic, inward dance not only explains the puzzling existence of hot Jupiters, those gas giants orbiting closer to their stars than Mercury is to our Sun, but also provides a perfect mechanism for delivering icy, volatile-rich building blocks from the frigid outer system to the warmer inner regions. These transported materials, the very stuff of comets and distant ice worlds, become the raw ingredients for both water-rich super-Earths and the gaseous envelopes of Mini-Neptunes. Scientists categorize this inward journey into different types, depending on the planet's mass and its interaction with the disk. Type 1 migration, for instance, typically involves smaller planets, perhaps up to 10 Earth masses, that are still deeply embedded within the gas and dust of the disk. These worlds exchange angular momentum with the disk material, like a small boat moving through a thick, viscous fluid, and can migrate inward relatively quickly over periods of hundreds of thousands of years. But for true giants, planets of many tens or hundreds of Earth masses, a more dramatic process known as Type 2 migration takes hold. These colossal worlds, like a supertanker plowing through water, carve out deep, wide gaps in the protoplanetary disk, clearing a path around their orbits. Once a gap is formed, the planet becomes locked into the viscous flow of the disk itself, moving inward along with the bulk of the gas. This process is slower than Type 1, often spanning millions of years, but it is incredibly powerful, capable of dragging even the most massive worlds from their birthplaces into scorching close-in orbits. This grand migration is a cosmic sculptor, shaping entire planetary systems into configurations radically different from our own. Consider the remarkable TRAPPIST-1 system, a compact family of 7 planets, all roughly Earth-sized and orbiting a cool red dwarf star. These worlds are packed so tightly that several of them are in intricate orbital resonance, a gravitational synchronization where their orbital periods are exact, simple fractions of each other, creating a kind of celestial clockwork. This precise, tightly knit arrangement is a strong indicator of past migration, a testament to how these planets formed further out and then migrated inward together, settling into a stable, resonant chain. It is a stark, almost dizzying contrast to the stately, wide spacing of our own solar system's planets, a reminder that our quiet corner of the galaxy is but one unique outcome in a universe of endless migrating possibilities. What does a planet truly look like when it defies every conventional expectation? When we move beyond the theories of their birth and migration, and instead focus on the physical reality of super-Earths and Mini-Neptunes, we encounter worlds that are far stranger, far more extreme, than anything early science fiction authors ever dared to conjure. These are not merely bigger versions of our own familiar rocky sphere, nor simply shrunken gas giants. They are fundamentally distinct classes of cosmic entities, each operating under bizarre physics and geology that turn them into natural laboratories of the extreme. Consider a water-rich Mini-Neptune, a world cloaked in a vast, deep atmosphere where the very concept of an ocean becomes an alien nightmare. The immense atmospheric pressure on such a world would be truly crushing, so profound that it would force water molecules into exotic phases of matter utterly unknown on Earth. Descend through its turbulent hydrogen-helium envelope, and you might find yourself in a realm of supercritical fluids, a state where the distinction between liquid and gas completely vanishes. It is a cosmic soup, where density fluctuates and molecules move with an unsettling fluidity, pressured into a state of matter beyond our terrestrial comprehension. Even deeper, approaching the planetary core, the pressure and heat could create forms of hot ice, like Ice 7 and Ice 10, crystalline structures of water that exist at temperatures far above boiling point, yet remain solid due to the overwhelming force exerted upon them, an inverse reality to the ice we know. In a thrilling recent development, the James Webb Space Telescope has begun to peel back the atmospheric veils of these enigmatic worlds. Its groundbreaking observations of worlds like K2-18b, for instance, confirmed the presence of methane and carbon dioxide in its atmosphere, crucial building blocks for organic chemistry. This data, analyzed by visionary astrophysicists like Niku Madhusudan at Cambridge University, strongly hinted at a Haitian environment, a term coined to describe worlds with massive hydrogen-rich atmospheres atop deep, water-rich oceans. Envision a world where a substantial portion of its mass is liquid water, trapped beneath an almost unimaginably thick, gaseous envelope, where light struggles to penetrate and pressures reach hundreds of thousands of times Earth's atmospheric standard. Such a world challenges our very definition of habitability, pushing the boundaries of where life might conceivably emerge. Now, shift your focus to a massive, dry super-Earth, and the scene transforms into a geological nightmare, a planet under siege by its own immense gravity. On our Earth, the slow dance of plate tectonics is the engine of geological activity, recycling our crust, building mountains, and regulating our climate through the carbon cycle. But on a super-Earth with, say, 10 times Earth's mass, the sheer gravitational pull could be so overwhelming that it would effectively suppress or even completely prevent this vital process. The result is a stagnant lid crust, a single, unbroken shell of rock encompassing the entire planet. Without the constant churning and recycling of material, the planet's internal heat would have no release valve. Imagine the consequences. Volcanic eruptions, instead of occurring in localized regions, could erupt on a planetary scale for millions of years, spewing unimaginable quantities of gas and dust into the atmosphere. This relentless outgassing, unchecked by tectonic recycling, would create oppressively thick, toxic atmospheres. A runaway greenhouse effect, far more extreme than anything ever conceived for Venus, could take hold, turning the surface into a molten inferno, trapping heat with devastating efficiency. Models suggest this nightmarish scenario for worlds like 55 Cancri E, a diamond-rich super-Earth orbiting incredibly close to its star. These are not merely larger versions of our rocky neighbors. They are fundamentally different geological and chemical entities, worlds sculpted by forces so potent they redefine the very possibilities of planetary existence. For years, the phrase habitable zone has ignited our imaginations. It conjures visions of distant, Earth-like worlds, bathed in the gentle warmth of their stars, where liquid water might flow freely across vibrant landscapes, nurturing the very seeds of life. This optimistic view, however, often overlooks a profound and sobering truth. The mere presence of liquid water, while essential, is far from the only requirement for the emergence of complex, intelligent, and especially spacefaring civilizations. What if the fundamental physics of the galaxy's most common planets, the ubiquitous super-Earths and Mini-Neptunes, inherently act as an almost insurmountable filter against such advanced development? Let us delve deeper into the colossal challenges posed by worlds with immense gravitational pulls. Consider a super-Earth, a rocky behemoth perhaps twice the mass of our own planet, where gravity could be significantly higher, perhaps even double that experienced here. Every movement on such a world would be an immense battle against an unseen force. The energy cost of locomotion for any animal, from the smallest insect to the largest creature, would be staggering. Imagine a human trying to lift their own weight, not just once, but with every step they take, day in and day out. The sheer metabolic demands would profoundly limit the size and mobility of any complex organism. Life, as we know it, would be forced into dramatically different forms, perhaps evolving to be incredibly squat, dense, and slow-moving, or adopting entirely novel biological structures to cope with the relentless downward pull. The very architecture of life itself would be radically different. Bones, for instance, would need to be far thicker and denser to withstand the crushing forces, or perhaps hollowed out and reinforced in ways we can barely conceive. The circulatory system, that intricate network of arteries and veins, would require immense pressure to pump blood against such a powerful gravitational gradient, raising fundamental questions about the limits of biological engineering. A heart on such a world might need to generate pressures many times that of a human heart, perhaps equivalent to the pressure inside a hydraulic press, just to circulate vital fluids to the brain. This is not merely a matter of being slightly heavier, it is a complete re-engineering of biological viability, but the challenges extend far beyond the biological. For any civilization to truly flourish and explore its cosmic neighborhood, it must escape its home world. This is where the concept of a gravity prison becomes terrifyingly real. Every celestial body possesses an escape velocity, the minimum speed an object needs to break free from its gravitational pull and travel into space. For Earth, this velocity is approximately 11.2 kilometers per second, or about 25,000 miles per hour. While a formidable speed, it is achievable with chemical rockets, as proven by decades of space exploration. Yet, on a super-Earth, especially one with a significantly larger radius and greater mass, the escape velocity could skyrocket to 20 kilometers per second, or even higher. The amount of fuel required for a rocket to reach escape velocity does not increase linearly with the velocity itself, it increases exponentially. To double the escape velocity does not simply mean doubling the fuel. It could mean requiring hundreds or even thousands of times more propellant. For a civilization trapped on a massive super-Earth, the engineering challenge of building a chemical rocket powerful enough to escape its crushing gravity might be an insurmountable barrier. The sheer scale of the vehicle, the colossal amounts of fuel, the destructive power needed for liftoff, could render space travel a near impossibility, effectively trapping any potential civilization on its home world, forever cut off from the stars. Then there are the Haitian worlds, those enigmatic mini-Neptunes shrouded in vast, deep oceans beneath thick, hydrogen-rich atmospheres. These are worlds where the very notion of a solid surface vanishes beneath an unimaginably deep, high-pressure liquid realm. What would the evolution of complex life look like in a perpetual twilight, or even complete darkness, where sunlight cannot penetrate the hundreds of kilometers of water above? How would a technological civilization develop without access to a rocky crust, the very source of metals and minerals essential for tools, electronics, and advanced infrastructure? Our own civilization, from the Stone Age to the Information Age, is built upon the exploitation of Earth's geology: iron, copper, silicon, rare earths. If the only accessible elements are those dissolved in a vast, dark ocean, or present in the atmospheric gases, the evolutionary hurdles for complex technology become truly profound. Could intelligence emerge and build advanced tools in an environment where even a simple campfire is an impossibility, and every resource must be painstakingly extracted from a high-pressure liquid? This intricate interplay of forces, astrobiology contemplating the forms life might take, biomechanics calculating the limits of biological structures, and rocket science defining the boundaries of cosmic escape, paints a far more nuanced picture of habitability. The habitable zone, that comfortable band where water can exist as a liquid, is not a cosmic welcome mat. It is merely the first, most basic filter. Beyond it lie myriad other, equally critical, and often far more restrictive, planetary conditions that could turn even the most seemingly promising world into an evolutionary cul-de-sac, a celestial dead end where complex life, let alone spacefaring intelligence, might never emerge. For centuries, we regarded our own cosmic neighborhood, this quiet stretch of space we call the solar system, as the definitive blueprint for planetary architecture. We built our models, our very understanding of how worlds form, based on the familiar order of our 8 distinct planets. Yet, as the universe has revealed its true diversity, populated by ubiquitous super-Earths and Mini-Neptunes, a profound and unsettling question has emerged. Why is our solar system so utterly unique in its absence of these common cosmic residents? Why did our planetary family form without a single super-Earth dwelling close to our star, a type of world found in 1 out of every 4 star systems surveyed? The answer, it turns out, lies not in a gentle, orderly beginning, but in a chaotic, almost violent epoch dominated by the largest planet in our domain, Jupiter. This is the story of the Grand Tack hypothesis, a leading theory proposed in 2011 by a team of astronomers, including Kevin Walsh, which paints a dramatic picture of our solar system's formative years. It suggests that young Jupiter, a colossal sphere with a mass over 318 times that of Earth, did not simply settle into its present orbit. Instead, it embarked on a colossal, destructive journey. This nascent giant, still surrounded by the swirling disk of gas and dust from which it formed, began to migrate inward, drawn by complex gravitational interactions within the protoplanetary disk. Picture a massive ship plowing through an ocean, creating a wake that pulls it forward. Jupiter, then in its cosmic infancy, surged inward, its immense gravity acting as a celestial wrecking ball. Calculations indicate this inward trek may have brought Jupiter as far as the modern orbit of Mars, a journey spanning hundreds of millions of kilometers from its likely birthplace further out in the colder, richer regions of the disk. As Jupiter plunged inward, it encountered the primordial planetesimals, the building blocks of planets that were already coalescing in the inner solar system. Its colossal gravitational field, a force equivalent to 35,400 Earths compressed into a single sphere, scattered these nascent worlds with ruthless efficiency. Many were flung violently into the scorching embrace of the young sun, destined to be vaporized. Others were ejected outwards, cast into the frigid, distant reaches of the system, beyond the orbit of Neptune. This cataclysmic sweep effectively starved the inner solar system of the raw material, the dense aggregates of rock and ice that would have been necessary to form a super-Earth. Without that abundant cosmic dust and pebble-sized debris, worlds like Earth and Mars could only form as relatively smaller, less massive rocky bodies. But Jupiter's rampage was not a one-way trip. The tack in Grand Tack refers to a nautical maneuver where a sailboat changes direction against the wind. In this cosmic analogy, Jupiter's inward journey was halted and then reversed through a complex gravitational resonance with Saturn, its younger, equally massive sibling, which was also migrating inward, albeit at a slower pace. When these two gas giants achieved a specific orbital alignment, a 2-to-1 resonance where Jupiter completed 2 orbits for every one of Saturn's, their combined gravitational pull reversed their course. This powerful duo began to spiral back outward, migrating to their current, stately positions in the outer solar system. Computer simulations of this chaotic history have beautifully illuminated several long-standing mysteries of our planetary neighborhood. Not only does the Grand Tack provide a compelling explanation for the striking absence of close-in super-Earths, the galactic norm, but it also accounts for the curiously small size of Mars. If Mars had continued to accrete material without Jupiter's intervention, it would likely be far more massive, perhaps rivaling Earth in size. Instead, it is a terrestrial dwarf, with a diameter of only 6,779 kilometers, barely half that of Earth, and a mass of just 10.7% of our home world. This miniature stature is a direct consequence of Jupiter having cleared away much of its potential building material. Furthermore, this dynamic model perfectly explains the perplexing composition of the asteroid belt, a ring of rocky and icy debris located between Mars and Jupiter. The Grand Tack predicts that Jupiter's dual migration, inward then outward, would have stirred this region profoundly. It would have flung inner, rocky asteroids outwards and pulled outer, icy comets inwards, resulting in the distinct mixture of dry and volatile-rich bodies we observe today. It is a cosmic fossil record, a snapshot of Jupiter's violent passage. Our solar system's architecture, this familiar, seemingly stable arrangement of planets, is not the product of gentle, orderly formation. It is, by this leading hypothesis, the dramatic and destructive legacy of its largest planet, a gravitational behemoth that cleared our neighborhood of what, elsewhere in the universe, would have been its most common residence. The cosmic stage, for generations, has presented a simple narrative. We, humanity, occupy a humble, unremarkable corner of an average galaxy. This notion, the Copernican principle, has anchored our understanding of the universe, teaching us that we are not special, merely orbiting an average star in an average spiral arm. Yet, the torrent of data pouring in from space telescopes, charting thousands upon thousands of exoplanets, has begun to redraw this self-effacing portrait. It reveals a startling, almost unsettling truth. Our specific planetary arrangement is, in fact, highly unusual, perhaps even a cosmic anomaly. This profound realization is not a retreat into pre-Copernican arrogance, but rather a more nuanced and humbling embrace of cosmic diversity. For centuries, our solar system stood as the singular template, the only planetary family we knew, defining what a normal system should look like. Now, confronted with a galactic census dominated by super-Earths and mini-Neptunes, worlds larger than Earth but smaller than Neptune, utterly absent from our own neighborhood, we must acknowledge that we are the exception, not the rule. This cosmic outlier status forces a fundamental shift in our perspective, transforming our quiet, familiar celestial home into a place of profound strangeness in the grand scheme of things. The next frontier in this cosmic recentering involves moving beyond mere planetary demographics, beyond simply counting worlds and charting their sizes. The grand challenge now is to understand the intricate chemistry and geology of these alien spheres, to unravel the physical laws that sculpt their bizarre forms. Future missions, like Europe's Project for the Long-Term Observation of Transiting Exoplanets, which uses the acronym PLATO, are designed with this ambitious goal in mind. PLATO, scheduled for launch in the mid-2020s, aims to characterize hundreds of rocky and icy exoplanets, identifying not just their presence, but their precise mass, radius, and orbital period, which are critical for understanding their internal composition. Similarly, Europe's Atmospheric Remote Sensing Infrared Exoplanet Large Survey, known as ARIEL, set for launch in the early 2030s, will take this quest to an unprecedented level. ARIEL will peer through the atmospheres of thousands of exoplanets, studying their chemical compositions in exquisite detail. Its instruments are capable of detecting water vapor, carbon dioxide, methane, and a host of other molecules, providing crucial insights into the potential for habitability or the presence of extreme, exotic chemistries. This deep dive into atmospheric characterization will allow scientists to move from statistical surveys to a true understanding of planetary environments, unveiling the full spectrum of cosmic possibilities. The very absence of a super-Earth within our own solar system, once a non-question because we simply did not know such planets existed in abundance elsewhere, has now become a crucial clue, a profound historical marker. It is a puzzle piece leading us to a deeper comprehension of our violent, chaotic origins, perhaps hinting at early planetary migrations or cataclysmic events that cleared our inner system of these common worlds. This void in our familiar backyard suddenly screams volumes about the unique forces that shaped our present. This prevalence of common yet alien worlds transforms our galaxy from a collection of potential Earth copies into something far more wondrous and bizarre, a veritable cosmic zoo. Instead of variations on a familiar theme, we find entirely new categories of planets, worlds of supercritical water, where liquid and gas are indistinguishable, or rocky bodies with stagnant, unbreakable crusts that prevent geological recycling. These are not just super-Earths or mini-Neptunes in name. They are fundamentally different classes of geological and chemical entities, each a natural laboratory for extreme physics and unimaginable conditions. In a universe teeming with these ubiquitous, strange, and often extreme worlds, our own solar system, with its wide-open spaces, its distinct separation of rocky planets and gas giants, and its curious lack of close-in intermediate-sized worlds, might just be one of the rarest places of all. The galaxy, once perceived as a sprawling collection of potential Earth-like havens, now reveals itself as a tapestry woven with countless threads of alien design. And in this vast, diverse cosmic fabric, our quiet, temperate home stands out not as the norm, but as an extraordinary, beautiful exception.